All right, good afternoon, everyone. Thanks for joining us. Looks like we're going to go ahead and get started. Roy, can you hear me okay on that end?
Yep, I'm here as well. Here, I'll tell you what, I'll launch the poll now here as well.
Perfect.
If you guys could just answer here if you're able to hear the audio or not here, just so that we know that we are broadcasting.
That would be great. Thank you for your help with that. Don't vote, Roy. And if we could ask the attendees if you can just go ahead and stay on mute, just to not interrupt the flow of the webinar, that would be very helpful.
All right, it looks like we've got almost all yeses here. I'll go ahead and close the poll.
Perfect.
So I think we should be good. Those of you who aren't hearing us, make sure you're not on mute or something like that, not muted your computer.
Yep. Awesome. All right, cool.
You wouldn't be able to hear me say that.
Exactly. Well, cool. Good afternoon, everybody. Thanks for joining us. A couple minutes after 2. We're going to try to stay within the half-hour time set. Thanks again for joining us. My name is Dan Petito. I'm an inside account manager here with Design Point Solutions. The other voice you're hearing is Roy Mutalik, and he's an application engineer here with Design Point. Hello back, Roy. And yeah, we basically excited to run through some stuff. Today we're going to be talking about SOLIDWORKS Simulation. The title is obviously pretty straightforward, predict your product's future performance with SOLIDWORKS Simulation. We're going to set aside some time at the end of the webinar to answer any questions that you guys may have. We certainly appreciate your questions, so we do ask if you could hold off on those until the end. Again, we will set aside some time to get those answered. Again, just in the interest in not disrupting the flow of the webinar. So next slide, please, Roy. So yeah, just a quick snapshot of the agenda. Basically, what is SOLIDWORKS Simulation? So Roy has a couple things queued up as far as, just kind of a deeper dive in terms of some specific functionality within simulation. But, if you're not familiar, obviously, SOLIDWORKS Simulation provides tools to test your designs and make the decisions necessary to improve quality. So, things like strength can be tested, safety, kinematics fully analyzed, and basically a wide variety of geometry types are supported. So you can simulate real-world performance and basically predict how your product will perform in a real-world environment. So as you can see here, just kind of a quick snapshot of the different capabilities within simulation. Specifically today, I know that we're running a frequency study as well as a linear static study. Roy has gone and modeled up a guitar, and we're going to be doing a frequency analysis on tensions in frequency and also run a linear static test to basically ensure that the guitar neck will not bend. So pretty cool study and some pretty cool stuff that Roy had put together to share with us. And, again, this is just kind of a quick snapshot of some of the different capabilities. And we picked out 2 for today's purposes that Roy is going to kind of demonstrate and walk through in more detail. Next slide, please. And designing a guitar. So, again, as I mentioned before, determine the tensions in the strings. We're going to apply that load to the neck and ensure it will not bend. And I believe that Roy is going to make some changes to the design, and based off of those changes, retest and validate those changes. So, Roy, I'm going to hand the controls over to you.
Absolutely. All right. So as Dan mentioned, we're going to go through sort of an interesting example here today. Guitar is actually one of my hobbies. I enjoy playing the guitar, so I like to try to integrate things that I enjoy doing here. Simulation is my other hobby. I do this in my spare time. I definitely enjoy the simulation part of the software. So I put those together right here for this demo. And what I'm going to do first is a frequency analysis in SOLIDWORKS Simulation. And what we're trying to determine here is how much tension we need in these strings. So just to give a little bit of background, these strings vibrate when plucked based on their natural frequencies. And depending on what frequency we vibrate the strings at, or they vibrate at rather, it's going to provide a different pitch. So that's what we're going to be doing here, taking a look at what frequency a string would vibrate at and how we can add tension to it to make it vibrate at a higher pitch to create the pitch that we're looking for here in this guitar string. So let's take a look at that. I'm going to jump over to SolidWorks here, and let's take a look at my guitar here. So this is what I've started to model here. I'm working on designing this, and I've got some strings put in there. They're just simple solids for now. Now let's take a look at one of these strings here. So this topmost string is my low E string. So on a guitar, the low E vibrates at a note of E, which happens to be 82 hertz. So we want to make sure that in the process of vibrating the string, it would vibrate at 82 hertz. So its natural frequency is 82 hertz. And that's what I'm going to analyze first by adding tension to the string until we achieve that result. So to simplify things a little bit, I don't actually need the whole guitar to do this analysis. I can look at just the string itself. So let me take a look at that here. I'll jump over to the model of just my low E string. Again, it's just a simple solid here, and that's what we're going to run our frequency analysis on. So SolidWorks Simulation integrates right within SolidWorks here. It's just at the top as a menu. So let's go ahead and define a new study here. And here are all my different study types. I'll go ahead and pick my frequency study and analyze the natural frequencies of this guitar string. So let's go ahead and set this up here. I'm going to go ahead and first just make sure I have a material applied to this here. And I'm just using a material that I've selected here. Guitar strings are really made out of sort of a combination of steel core wound with nickel on the outside there. So I've just kind of created a material custom there to try to map those properties as closely as I could there. Realistically, maybe we'd want to actually model the wound core geometry there, but for this case, we'll just go with the simplified version here. What I'm going to do in this study is fix one end of the string here, just by simply applying a fixture to it here. And we're going to apply tension to this here by using a force. And I'll rotate this guy around, and we'll pull on the other end. So pulling on it from this flat face like this is going to apply tension, and I'll flip the direction to make sure that I'm tension here, not compression. And let's start with some value. I don't really know what the number should be, but maybe we'll say 15 pounds of force is what we're going to pull on it with here. And we'll give that a try there. Now, SOLIDWORKS Simulation is a finite element analysis tool. So what it actually does is it breaks it up into a mesh, my geometry into a mesh there of finite elements. And then it's going to solve a series of creating a stiffness matrix and a series of differential equations to actually output my results here. I'm going to automate that meshing process here just using my auto mesher there. And I can actually tell it to mesh and run simultaneously right here. So we'll go ahead and see that when I hit this button. It's going to mesh the model, and then it's going to go ahead and run and solve those differential equations. And here, in this case, it will output for me my vibration here, the natural frequencies of this string. So what we can see here, it shows a displacement plot of sort of how the string would be moving. So if I animate this, you'll actually see this guy wiggling. A note, it is grossly over-exaggerating how much it actually would move there, just to give you an idea of what's actually going on. So you can see how that's kind of flapping how you'd expect this guitar string to do so. It's listing for me currently 5 different modes. So we can have many different natural frequencies to this here. And looking at each of these individually is showing a different mode. So if I look at this one here, this is going to be sort of flapping vertically there. It's going up and down. So without going too much into the details of it there, we can look at our mode shapes from our results right here. So I'll go ahead and right-click on my results folder and list my resonant frequencies here. So here we see a nice table calling out those resonant frequencies. And as I was showing, and as I would expect to see with this, we can see they're kind of coming in pairs here, frequency of about 75 hertz, 74.1 hertz, and there's a vertical and horizontal pair. So then even our next natural frequency has that vertical and horizontal pair there. The key with this, though, is that the string is always going to vibrate at the lowest natural frequency there. So really all we need to look at is our lowest frequency here. So mode number 1 is all that's really going to matter to us. We could even look at our mass participation in that to show that here. Basically what these numbers are showing is that our lowest modes are the most participated modes, and therefore the ones that the string would be most likely to vibrate at. So again, we just are looking for one mode in this case here. So 15 pounds of tension here is causing our mode here to vibrate at about 75 hertz. So that's great, but let's see, we need to hit that mark of 82 hertz to get that note correctly. So let me change my value here a little bit. Maybe we'll try 20, and I'll rerun this study. And we'll see a change in result. Now it looks like we're at 85 hertz here. So we've overshot it a little bit. So this will give you an idea of how we could kind of find what that value needs to be. Going through and changing our tension values until we can really find narrow down to that frequency result there of that 82 hertz. So it's great. It's not difficult to go in and keep changing that, but there's a better way of doing that, and we're going to take a look at something called a design study here in SOLIDWORKS. Just going to really automate the process for us here. So what I'm going to do is tell it that the force that I'm applying here, the tension, is a variable, and I want to allow it to change that and run the study each time, output the results for me here. See if we can figure out what's going to give us close to that 82 hertz frequency. So I'll go ahead and just define a design study here quickly. I need variables in that, so let's go ahead and define a variable. And it's going to be a simulation variable here, and I'll just name this tension. We'll give it a value here. Maybe we'll start it at 15. And now we need to go ahead and apply that load and link it to that variable here. So in our study here, I'll edit my load, and I'll tell it instead of to be 20, it should link to that variable. Oops, looks like I didn't save it here. Let's just redefine it here. Sorry about that. I kind of did that in a bad order here, so it didn't pop up for me. But now we'll see that that force one is here. All right, so we've linked it to that variable. Now in my design study, I can go ahead and choose to use that as a variable here. So the one I want to use is named force. I'll tell it what I want it to do is to range with the step, and we'll start at maybe 15 pounds, and we'll go to a maximum of 20 pounds. We know 20 was overshooting. And for now, let's just go with a pretty coarse step of 1 pound each time. So what it's going to do is run it at 15 and give me my results, and then increment that by 1, then run it at 16 to give me my results, etc. here. Now, we have to also tell it how we want it to terminate this optimization. So how do we know when we've hit our results? So I'm going to add something here called a goal. And what I'll do with this is say it's a simulation property of frequency, and we want the natural frequency of the first mode here in hertz. So I'll read that. I want that to be exactly 82 hertz. So that's how we're going to tell the design study here when it should be marked as complete. That's sort of what we're going for here, and it's going to pick from my results accordingly based on that criteria. All right, so we'll go ahead and run this. Oops. Oops, I've got something missing in my links here. Let me just check my parameters. I somehow have a duplicate here. Let me let's just get that design study up again here. So again, 15 to 20 with a range of 1, a step of 1 here. And let's see if we can add that goal now, the sensor. There we go. Now it's running for me. So what it's going to do here is it's actually going to process each scenario one by one, and you can see it's going to start giving me a results view here, where it's actually varying that force, and it's going to spit out here a frequency value accordingly. So this will just take a minute to tick through here. It's running 8 different scenarios, it's saying here. Again, I told it just to increment by 1 for our start here, and we'll see how that frequency goes up here. So looks like at 17 pounds force, we're still at 78. 18, we're getting close there at 81. And 19 is over here. We've overshot it now. So we're going to be somewhere between 18 and 19 pounds, and it's actually pulled for me that 18 was the one that it ran here that was closest to the result. So let's go back to our table view here, and now maybe this time what I'll do is change it a minimum of 18, a maximum of 19, and let's do a step of something less here, 0.1, and rerun this guy here. So we're kind of narrowing in on it this way here, going much smaller in our region, and this is going to run, should be a few iterations here. It always starts by doing the minimum and maximum, so that's why we have as many iterations as we have here, and it's going to plug along through all of those. It will just take a minute here to do that. We'll see the results shortly. Let's see, 18.4, we're at 81.91 hertz there. We're pretty close. And now at 18.5, it looks like we've overshot it. So we know that our tension now is somewhere here between 18.4 and 18.5 pounds force is what it's going to take for us to achieve that 82 hertz natural frequency for our lowest mode there. So from this, we've effectively been able to derive what the tension we need in the string for this given size is to be able to create the correct note when I pluck my guitar string there. So this is sort of a great example here of how we can look at our natural frequencies, what we can kind of get out from those there. So next what I'm going to do here, I've got that result for the load, the tension load. I've got 6 strings on this though. I want to make sure that as a result of applying that tension load for 6 different strings, I'm not going to end up bending my neck over. For anyone who does play guitar, obviously, you would know that if the neck bows forward, that's really bad. It's going to make it very uncomfortable to play, and it's just it's bad for your intonation as well. So you're not going to have a great guitar if it's bowing forward. So let's make sure that that doesn't happen with my design here as well. So that's what I'll do next, taking these kind of results. So I'm done with this string here. I'll go ahead and close that one out. And let's jump back to our guitar itself here. So for this simulation, I'm going to use a linear static study type. The idea being that I just have a prescribed load that's being applied to this solid, and we want to see what displacements come out from it, what stresses come out as a result of that here. So this is going to be a different study type that we run for this one. I'm going to go over to my configurations tab, and I've pre-created here a for simulation configuration of this guitar. And it's just removing the strings for me there. I don't need the strings on there to be able to test if the neck is bending. So that's all I did there. Just simplify my model a little bit. So let's go ahead and define a new study here. And this is going to be my linear static study. Let's go ahead and check and make sure that my material is applied correctly here. So what I'm going to use here is a material for wood, the material that it's made out of. And in this case, I'm using a linear elastic orthotropic material, which is available in SOLIDWORKS here. The definition of that is just something like wood has different properties in different directions. So if you're pushing it along the grain versus against the grain versus perpendicular to the grain, you're going to see different strength characteristics of that wood. So we can accommodate for that by having different Young's moduli for each of these here, X, Y, and Z direction there. So I just got to give it a reference so that it knows how to orient that. So I'll just go ahead and use the front plane so that it knows which direction X, Y, and Z is there. And I'll apply that material to it there. So my whole guitar now is made out of wood. That's exactly what I'm looking for here. All right, let's go ahead and fix this guy for starts here. I'm going to just fix it on the back there. I just need a fixture so that it doesn't take off in space when I go ahead and apply the tension to the neck. We don't want our guitar flying away. And how I'm going to load this guy is based on a force. Now, realistically, we would have tuning machines in these holes, and that's what the strings would actually be applied to, applying some tension sort of in this direction here, coming up a little bit. So what I'm going to do to simplify this a little bit, rather than putting in those tuning machines, I'm actually going to put the force right in the holes, and I'm going to use a selected direction based on this sketch here. So just giving it that kind of angle I'd like there, just so that it's not exactly flat here. Really, that would be kind of pulling up and bending the neck over like this a little bit. So we're simulating that with that selected direction there. And I'll apply the force, and I'm going to over-exaggerate this a little bit here, and I'm going to do 20. We found that value to be somewhere between 18.4 and 18.5. So let's play it safe here and put in 20 pounds force there. And I'm making sure to select here per item so that we know it's per each hole it's going to apply a force of 20, not a total. All right, and that should be all we need here. I'm again going to allow it to automatically mesh. I'm not playing with any of my settings there, so I'll just go ahead and allow it auto mesh and run there. And it'll take a couple of seconds to run through. And we'll see some results as a result of that loading now. So let's take a look there. Our stresses look pretty low, but let's look at our displacement plot over here on the left. Now we can see a pretty large displacement here. I will note these plots are exaggerated as well, just so that you can see how it's deforming. But looking at my legend over here, it looks like our maximum displacement still is about 15 millimeters. So just to show that here, I'll switch my plot really quick to true scale, so it'll show on the model really what 15 millimeters is. And it's not as huge as we were showing before, but there's some definite bowing to that neck. And that would cause our intonation problems. It would cause our distance between the string and the fretboard to be too high. So we definitely don't like that by looking at that change here in that neck. So we sort of have a bit of an issue there as a result of this. That wood is just not quite holding up for us as a result of this loading that I derived from the tension in the strings. So I'm seeing here a potential issue. So looking at that applied load, it does appear to be causing some kind of a bowing to it. So my next step here is I want to make some changes to the design to prevent this from occurring in my actual prototype. You know, when I really build this guy, I don't want that to happen. So how can I change that? And sort of simultaneously, I'll show you how quick and easy it is within SOLIDWORKS Simulation to retest and validate your changes. You know, really show what those changes did to your simulation results, your stresses, your displacements. Very, very quick to do. So let's take a look at that here. So let me jump back to my model of my guitar here. So this is a solid wood neck currently. It's just wood through and through. But really, guitars actually have something called a truss rod running right through the middle of the neck. And what that truss rod is it's actually a metal bar with the purpose of stiffening the neck so that it doesn't bow. So I've modeled here another configuration that has a truss rod. And if I take a look at this guy here, we'll see that we have that metal bar going right through the middle of the neck. And it's sort of coming out the other side as well. You can just see it's just a metal bar. Again, the purpose of that is really just to stiffen it and prevent the neck from bowing, just as we're seeing here. So let's see what result that adding that truss rod does to my design here. Instead of using just a blank wooden neck there, adding that truss rod should make a huge difference. So what I'm going to do is duplicate my static study here. So I've already got everything defined. So I'll just right-click and say I want to duplicate it. And this time I'll do it based on my configuration that has the truss rod in it here. So rather than using the one that doesn't here, we'll just use this guy here. And we can see when I do that, my fixtures, my loads, everything comes across exactly as it is there. Let me just verify my materials here real quick. Make sure that I have everything applied correctly. There's that wood. And check that my truss rod here, in fact, looks like I'm missing a material. So let's go ahead and apply here that material for this one as well. Just plain carbon steel maybe for that truss rod. Nothing special. All right. I've introduced another body, so I just got to do one thing real quick here. And I'm just going to tell SOLIDWORKS how it should handle those. So I'll just tell it to make sure to treat them as if they're bonded together. Don't worry about seeing those penetrate through each other. This is fairly standard here, just telling it how those bodies interact. Just with a simple click, it handles it for the entire assembly of components. All right, I'm still applying that 20 pounds per tuning machine there, and we'll go ahead and run this study. And it'll take a minute there to mesh and then solve, and we'll see the results there. So what we can initially see here, it does look like our stress values have gone up slightly, but as a result of that, actually, if we take a look at our displacements, my displacement is now at a maximum of 1.4 millimeters. So adding that truss rod has really added quite a bit of stiffness to this neck. Instead of that 15 millimeter displacement, we're seeing less than 2 millimeters. And if I edit the definition of this plot here, what I can do is show this in true scale as well. And I'll sort of look at it from the profile there. And we can see much less displacement there. My neck looks very straight. It is going to deform some amount. I mean, we're applying more than 100 pounds of force going back in this direction here. So we're going to see some displacement there, but 1.5 millimeters is over the full length of that scaled neck. Much less significant there, and this guitar will be playable as a result of that. All right, so making those design changes is easy as creating them in your SOLIDWORKS model, and then you can easily duplicate studies and rerun based on your same setup there. So it's really quick and easy to be able to do those, to make your design changes just the way that you're accustomed to, maybe in SOLIDWORKS, and to retest and validate there. There's no exporting of these models or anything like that. It's all done right within SOLIDWORKS and its simulation add-in there. So that's what I've got to show you here. Just two different study types again there, frequency and the linear static studies there. And we were able to now verify that this guitar is probably ready to get going here. So I'll kick it back to Dan here with that.
That was awesome, Roy. Yeah, thanks for running through that. And it looks like we have a couple of questions coming in. Appreciate your questions. We'll get to those in just a minute. Thanks for your question, Alex. So yeah, just to kind of summarize the benefits of simulation, as you may be able to kind of guess is what some of those might be, right? So some of the benefits, reduce prototyping costs, and/or outsourcing costs. So obviously we run into a lot of instances where companies are outsourcing these particular studies, or they're just doing internal prototyping. Obviously, there's a lot of benefit to be able to identify these potential issues earlier on in the design process. Perfect example with Roy and the guitar, right? So he made some changes to the guitar and the design. The neck, as you saw, was bending dramatically. So basically, what Roy was able to do is adjust the design to include that truss rod and present the neck from bending. Obviously, a lot of great value there. Shortened time to market. Obviously, improved product efficiency, boost product innovation. So, again, a lot of value in being able to, virtually run some of these studies earlier on in the design process to determine how your products will perform in a real-world environment. So, definitely some great examples. And everything you actually saw here today, the linear static capabilities are available in SOLIDWORKS Premium. And the frequency studies are included in SOLIDWORKS Simulation Professional and Simulation Premium. Am I correct in saying that, Roy?
Yep. Yeah, the SOLIDWORKS Premium was the linear static, and then the frequency is in Simulation Professional.
Yep. Awesome. Awesome. So, yeah, I guess, if we want to take a few minutes now, I'm seeing some questions come in. So let's see, Alex, your question. Could you apply this kind of material property along a nonlinear path like a curved surface with thickness? A material with a different modulus. Are you seeing this question in front of you, Roy?
Yep. So I think what he's asking about is the orthotropic material there, where the properties are different depending on sort of the direction it's going there. Yeah, this is really this is a simplified version of it here within what I showed you with the linear static study type. There is some functionality to be able to do more complex material types like that in the nonlinear module there, which is assuming a nonlinear material material properties there. Some of the assumptions that we're not making basically in the linear static will be covered with that. And there's also a composites module that will allow you to do something similar to that as well. So I guess in short, with what I showed today, no, but there is a way to do it.
Awesome. Appreciate your question, Alex. And, obviously, questions that don't come up now that you guys may have, at some point later today or, as you continue digesting some of the material that we went over today and Roy demonstrated, certainly feel free to reach out to us, give us a call, shoot us an email. Obviously, we're readily accessible. So any questions that you might have, I see a couple others coming in. Let's see. Roy, I'm not seeing my questions pane in the webinar. Are you seeing it okay?
I'm having a hard time with it as well. There's one I'm seeing.
Sure what happened.
Can you use your design study? In your design study, can you use a goal seek in order to find your desired frequency exactly? Yes, there is a way to do that, but you have to define a constraint. So with something like this, it got a little bit more complicated, which is why I kind of had pulled that from there. It gets a little bit just more consuming, but basically, in short, yes, it is possible, and that sort of is the end goal of a design study, is that you give it an exact value and you tell it, hey, figure out the number so that you can get it there. But yeah, defining those things got a little bit time consuming, and I didn't want to lose anyone in the process, so I had kind of pulled that from it there. Let me see. Was there another question here as well?
It looks like it was not a question. It was David Parker thanking us. Yeah, you're very welcome, David. Thanks for taking some time to join us. We appreciate that. Yeah, and again, if there are any more specific questions, again, that we weren't able to cover today, obviously there's a wealth of capabilities within SOLIDWORKS Simulation. So, again, any questions that kind of come up as you have some time to absorb some of the content that we went over, feel free to reach out, give us a call, shoot us an email. Again, we're happy to get those answered. Oh, yeah, thanks for that, Roy. I meant to include that. But it looks like there aren't any other questions.
I just threw Dan's email up there down below his name, so feel free to shoot him an email. He'll get it forwarded to me, or make sure we get that handled for you here.
Sounds awesome. Sounds awesome. So you're not going to play a guitar solo for us this afternoon, right?
No, unfortunately not. Sorry about that.
Save that for another day. Well, thanks again, everyone, for your time. We really appreciate it, and we'll see you next time. Have a great afternoon.